Thank you.
Hi, I'm Sergey from Replica.io, an open source project set on making a breakthrough in designing and implementing distributed protocols for the future of decentralized computing. Please bear in mind that some stuff that I'm gonna tell you is speculative and maybe opinionated. I'll skip this, but tell you a few words about this project I've been working on. Replica.io will be a framework with all we need to design and implement core mechanisms of distributed platforms like consensus in blockchain in a simple, flexible, and reliable way. It's being developed entirely in the open from day one, and it's still in early research. I've been searching for better ways of specifying and implementing distributed protocols, so I did extensive research and shared my findings on the project's blog. Slides are different. Okay. So I guess you heard that distributed protocols are hard, and it's largely due to their concurrent nature. But concurrency alone is very tricky. Concurrency is difficult because it introduces a lot of non-determinism, so we have to reason about all possible orderings of events, and it's easy to make subtle mistakes that are hard to find and fix. So it's tempting to try avoiding concurrency as much as possible, and making most of the code sequential. But doing this means introducing some excessive extra synchronization that may cause unexpected issues like deadlocks or resource leakage. It also makes code awkward, complicated, obscure, and fragile. When we are thinking, we focus on one thought at a time. We communicate with linear sequences of sounds or symbols, including computer programs. So a sequential model of computation is very intuitive. It even seems natural. But the real world is not like that. It's fundamentally concurrent. So is foundational software in decentralized distributed systems. It's inherently concurrent. So I've been wondering if there is a natural way to approach this complexity with confidence. What if maybe we should rethink concurrency in distributed systems from the first principles and approach it fundamentally differently? Okay. Science like physics and information theory are all about fundamentals of the real world, so maybe we can take some inspiration from there. One of the most important principles in physics is conservation, and it also applies to information. If we think of the universe as a whole system, it's a closed system. As a whole, it's a closed system. By definition, there is nothing outside it could interact with. But anything else is an open system, a part of the universe surrounded by the environment. Information in the universe is conserved. So information always comes from somewhere, and it eventually goes somewhere. We can think of this as information coming into our system from its environment, redistributing within the system, and then going back to the environment. We should also keep in mind that real systems are fundamentally bounded. They cannot grow infinite. In other words, to take in some new information, they must get rid of some old information. Now let's look at non-deterministic and irreversible computations. When there are multiple possible outcomes of a computation from the same input, we can think of this as the environment making a choice, which is a piece of information. So non-determinism is hidden inflow of information from the environment. Likewise, If we cannot restore the exact input from the output of a computation, then we must be losing some information, kind of dissipating it into the environment. So irreversibility is hidden outflow of information to the environment. Look how closely they are related, like mirror images of each other, duals. Another important principle in physics is locality, which basically says that interactions can only take place in the immediate surroundings. This guy had serious concerns about what he called spooky actions at a distance. And you know that was not without a reason. So special relativity implies that we cannot stop the world and take a snapshot of its state. There are space-like separated events that are truly concurrent. So there is no unique global view on a state of a distributed concurrent system, only local views depending on our frame of reference, namely where we look at the system from. Those local views, however, must be consistent. Luckily, that's what we actually care about. Now, how to apply all this to distributed and concurrent systems? Here's where the speculative part begins, the idea of reversible deterministic concurrency. What if we specify and implement our protocols by connecting together components that are highly concurrent, but conceptually deterministic and reversible? With non-determinism and discarding of information, making them explicit, while treating concurrency implicitly as emerging naturally from data availability and the system structure. Speculating on potential benefits, this may help to improve modularity and composability, enable compositional reasoning, eliminate hidden data flows, remove excessive synchronization causing fewer deadlocks, provide better control of resources like memory, enable enhanced debugging, and maybe even give rise to some new verification methods. So I started to develop this into something more concrete, and you can find the first results in the latest blog post on the project's website. So now I have to jump through the next few slides to just give you a glimpse of what it looks like. There we have concurrent, pairwise complementary inputs and outputs as the only means of interaction with some graphical notation. The notion of interaction lines as those pairs chained together with two kinds of interaction along and across them. Demand and availability for flow control. Some tricks to account for non-determinism. Synchronization when we need it. Delays and timers. Composite connections that can be rearranged. Some notation for repetitive patterns. A kind of recursion. We'd represent the system as a whole and then derive local logic of individual nodes, applying compositional reasoning and modeling different kinds of faults, hiding complexity inside components. There are some examples. And of course, still lots of open questions like how to formalize this, come up with a convenient textual notation, express this effectively in real code, in Rust, understand it's all the ups and downs. So here's what I would like you to reflect on. Distributed, decentralized systems like real world are inherently concurrent. Concurrency is hard and perhaps needs a more natural approach. There are some helpful physical principles like conservation laws, resource bounds, locality, and relativity. Non-determinism and irreversibility are dual and represent hidden flows of information. And now there is this idea of reversible deterministic concurrency, which who knows may help us to really make a breakthrough in designing and implementing distributed protocols. If you're interested, you can visit the website and learn a bit more about the project. And I would like to thank Blue Yard for taking me into the DOR funding program, which helped me sustaining the effort since September last year. Now the project needs to move forward, and if you have an idea of how to get funding for this stuff, please let me know. Thank you.